So we just learned how to plot different values of predictor and the response in a graph, and how then to interpret these values. But the challenge is that in the real world, the data is often highly variable and noisy. Our first participant may have a BMI of say 20 with a systolic blood pressure of 120, and second person might have a higher BMI 25 with a slightly lower systolic blood pressure 110. Another participant might have even higher BMI 30 and much higher systolic blood pressure 140. And as you see in the fifth participant, he has a higher BMI than the preceding participant with a BMI of 35, but had a lower systolic blood pressure than the preceding one. Now, if we plot all these values on a graph, they will be quite irregular, right? And now is the challenge how to draw a line across them. You might have this line which be the best fit to these values, or maybe this one or another one. So it is difficult to see which one of these will represent these dots more closely. The procedure or the method used to determine the best fitting line is called ordinary least squares, or OLS, or sometimes it is simply called least square method, which identifies the regression line and that minimizes the sum of squared residuals. And the residuals are in fact the differences between the observed and the predicted values. For example, for this red line, which is predicting the values of systolic blood pressure at different BMI levels, we see that at almost 20 millimeters of 20 BMI, the predicted systolic blood pressure is 110, but the observed was 120. So there is a difference of plus 10 millimeters of mercury. So we put our difference here 10, and the squared difference is 100. For the BMI of 25, we see that the observed systolic blood pressure was in fact 10 millimeters below that of the predicted systolic blood pressure, which was in fact probably close to 130 or so, but the observed was much lower. So the difference is 10. So we square it, minus 10 gets 100. For the person with a BMI of 30, we have in fact the observed value 2 above that of the predicted, so the square is 4. For the person with BMI 35, our predicted value was 18, lower than the observed, which squared the value 18, which comes down to 324. And for the person with BMI 40, we have the observed value 5 millimeters below that of predicted, and we square it to get the value 25. And then we add all of these up and we get the value 553. We do the same for say yellow line. In this case, we get a slightly lower value, that is 454. Again, we repeat the process for the third line, the green line, and this time we get the lowest value, 399. So of the three lines that we calculated, this squared difference 553, 454, and this time 399. So 399 is the lowest value, and so we conclude that this is the of these three lines, this is the best fitting line, which because it has the least square distance from the observed values. Of course, this process is handled by a computer, and of course it is much more complicated than the one which we are doing. The computer can do thousands or millions of calculations per second compared to us, which will be much slower. But I just wanted to show you the process which computer does to find the best fitting line to the observed values. So again, the green line, this line C, is chosen as the best fitting line because it has the smallest total squared error, which was 399. And once we have the best fitting line determined by computer, rest is just business as usual. We just determine how much is the increase in say our outcome of interest, which is systolic blood pressure in here, with each unit increase in your exposure outcome, which is BMI in this case. Since the intercept was 80 and our slope is 2, which means that with each unit increase in BMI, there is 2 millimeters of systolic blood pressure rise. We can now determine the BMI of the systolic blood pressure of respective BMI. For example, if a person is having a BMI of 25, we can just plug in the values, intercept 80 plus 2, that's the slope, times 25, that is the BMI, which if we sum up, we get the value of predicted or the estimated systolic blood pressure for a person with a BMI of 25 to be 130 millimeters of mercury.